Okay, so with that out of the way, we can get going, and this is now being recorded onto YouTube. And again, please, if you haven't already, please mute your mics. Okay. So this is an introduction of who I am. If in case this is your first lecture, my contact email is here in the bottom. If you ever want to email me with any questions or anything regarding the course, the MCAT, or anything at all, please feel free. This is the description of the course. It's a 15-week course, and we're on week 8. 3 lectures per week, Thursday, Friday, Saturday, and 1 office hours on Sunday, all beginning at 8:30 p.m. Eastern Standard Time. We also have a GroupMe for this course. The GroupMe will have all the lecture recording links and PowerPoints posted. We'll also be posting any updates or changes to scheduling there as well. It's also a great way to get a hold of me or any of the other tutors if you want to ask any questions about the course, the MCAT, or anything at all. There's also a bunch of students in there. I believe we're over 400. So I'm sure somebody has an answer for you in that chat if you have a question. David, the other tutor with me, will be posting in the chat, and he'll be also monitoring the chat if you want to type any questions in there as well. Okay. Learning objectives for today. First, we want to know how can we define acids and bases. So there are actually multiple definitions of acids and bases that I'm sure you've heard about in your undergraduate college career. And we're just going to go over all 3 of them and what the differences are. We're also going to talk about what the key properties of acids and bases are, mainly pH, pKa, things like that. We're also going to be talking about how we can measure acidity and basicity. Again, that goes along with pH, pKa, and all of that. Lastly, we're going to be talking about titration and how we can measure changes using titration. Okay. All right, so we're moving on to the content. First, we want to talk about the definitions of acids and bases. So there are 3 main definitions that I'm sure you've heard of before. The most common one is the Arrhenius definition, which focuses on the concentration of H+ and the concentration of OH-. This one's very simple. HCl is an acid, NaOH is a base because NaOH gives up its OH. HCl gives up its H. Very simple. Then there's the Bronsten Lowry definition, which focuses on protons rather than specifically H+ and OH-. If you know, H+ is a proton, so the definition of acid is actually the same in Arrhenius and Bronsten Lowry, pretty much. But the difference comes in Arrhenius. The difference comes in bases, where in Arrhenius it says it's specifically something that has OH-, whereas in Bronsten Lowry it's more on a proton acceptor. Okay. And then lastly, it's Lewis definition, which is the most different and the least commonly used in this sense. And it focuses, instead of protons, on electron pairs as donors and acceptors. Okay. We'll go into detail in each one. Firstly is Arrhenius. This is the classic definition and focuses on OH- and H+. Acids are molecules that can increase the concentration of H+ in solution. Bases are molecules that can increase the concentration of OH- in solution. Classic examples: HCl dissolves into H+ and Cl-, NaOH dissolves into Na+ and OH-. By dissociating and in a solution, you increase the concentration of H+ because at the start you had no H+, you just had HCl and say water, and then once it dissociates, you have a lot of H+. NaOH dissociates into Na+ and OH-, so again, it increases the concentration of OH- in the solution. The strength of the acid and base is typically dependent on how easily it dissociates. So for example, HCl dissociates pretty easily, so it's considered a strong acid and base, whereas something that doesn't dissociate as strongly would be considered a weaker acid or base. Okay, very simple and straightforward. Next, slightly more complicated, is the Bronsten Lowry definition. This is probably the one that's most tested and the most common one that you'll be seeing, and it focuses rather on protons. So acids are molecules that donate protons, while bases are proton acceptors. right? And if you know, hydrogen is made up of 1 proton and 1 electron, right? Whereas we said in the Arrhenius definition, a proton is we use H plus. H plus means that you have 1 more proton than electron, so that just means you have 1 proton. So it's essentially H plus is just a proton. And it's exactly the same as the previous definition. An acid is just something that gives up an H plus or gives up a proton or increases the concentration in solution. Bases, however, are a little bit different. A base is anything that can be a proton acceptor. OH can also qualify as that because it can be an acceptor, but there are other things that don't even have an O or an H that can also qualify. For example, CH3COH is a very common one that you'll see, a very common acid that you'll see. And it's an acid because the OH here or here can be deprotonated into COO minus and H plus, right? So this would be the same, and this would just become O minus, this would just become H plus, and this bond would be broken. Again, dissociation just like with HCl. And then this proton gets donated away. This, however, is a common example of a base, right? And the reason for that is because the NH2 can be protonated into NH3 plus. If you can see here, it has this lone electron pair, which means it can act as an acceptor, right? An H plus or a proton can attach onto here and now form a bond. And now you have NH3 plus instead of NH2 on this end, right? And it still touches carbon. That can also that's what's considered a base by this definition. Doesn't have any OH. It doesn't have any OHs, just like NaOH would, but it's still considered a base because it's a proton acceptor. And the way you can kind of connect these two definitions is in water. If you put a base into water, so for example, if you put this into water, if it's a strong enough base, it'll actually take the hydrogen off of water and it'll turn water into OH minus, and it itself will become protonated into NH3 plus. And in that sense, it could increase the concentration of OH minus in solution, right? By taking the H away from the water and turning it into OH minus. Does that make sense? Okay. Oh, and I do want to mention this specifically with this definition because this definition is the most common and most well tested. So if you notice here, we have the same exact molecules, the acid and the base. And when you just put them in solution together, they can work together. One gets deprotonated, the other gets protonated, an acid-base reaction. Right? Once a base is protonated, it actually becomes an acid. And once an acid is deprotonated, it becomes a base. So if you can see here, this is what happens when you deprotonate this acid. And this is what happens when you protonate this base. Now, if you look at it, this is now an acid because it can no longer accept any more protons. It's already full. But now it actually has an extra proton that it can give away, thus making it an acid. This, again, now has no protons it can give away because it already gave away all its protons, but it has this spot where it can accept a proton now, thus making it a base. So you see, once an acid deprotonates, it becomes a base. When a base protonates, it becomes an acid. A strong acid always has a weak conjugate base, and a weak acid always has a strong conjugate. A strong acid always has a weak conjugate base. A weak acid always has a strong conjugate base, and the same applies in the other way. The reason this is if you have a strong acid, so say, I don't know, HCl or some strong acid, and it gives away its H plus, it very easily dissociates and gives away its H plus. It's very happy to give away its H plus. Well, now it's a base. It's just Cl minus, which is a base, right? Because it's a proton acceptor, but it doesn't want to take back its proton, right? Because it was happy. It was very easy for it to give away its proton. It doesn't want to take it back. So it's not very good at it. The Cl minus is not very good at taking its protons back and acting as a base. Whereas if something's a weak acid, it's very reluctant to give up its proton. It doesn't want to give up its proton, but if you force it to give up its proton, it will. But it becomes a strong base because as soon as possible, it wants to take its proton back because it wasn't comfortable giving it away in the first place. So if you're a weak acid and you are forced to give up your proton, at the first opportunity given, you'll want to take it back and act as a base. And that's what makes you a strong base, because you very easily accept protons. Does that make sense?
Mark?
Okay. Yeah, please. Go ahead.
Yeah, sorry, this is Taja. Can you please just reiterate what's protonated and deprotonated again? I remember it from like CHEM, but like that was like 2 years ago for me.
Sure. So protonated and deprotonated means protonated means you added a proton, right? Protonated. Deprotonated means you removed a proton, so it's deprotonated. It was unprotonated. So this acid is protonated, right? This is, or when you look at the acid and its conjugate form, so these are the two forms of the same molecule. You see that, right? Well, this is the protonated form on the left. This is the deprotonated form on the right, because the form on the left has its proton attached to it. The form on the right doesn't have its proton anymore, so it's deprotonated. Bases, it's the same thing, right? So bases, this is the deprotonated form because it doesn't have an extra proton, it just has its like normal stuff, and it still has an extra spot left over. And over here, it now is protonated because it now has 3 H's, right? It received an extra proton.
Okay, so when you say, sorry, so when you say you just think hydrogen, don't think of that. Well, electrons obviously aren't protons, so just think hydrogen, don't think anything else.
Exactly, yeah. In protonated, you think hydrogens, essentially. We're going to talk about the next definition in a minute, which is the Lewis definition, which you actually do think about electrons. But for this definition, you only think of hydrogens. And just a way to think about, just like a thing to remember, bases are pretty much always deprotonated, whereas acids are protonated. So if you saw here, this was the deprotonated version, and it's a conjugate base. And in this one, this was the deprotonated version, and it's a base. Whereas this and this were the protonated version. So acids are always protonated, bases are always deprotonated. That makes sense. Opal, you have a question?
Yeah, if we go back. Okay. If we go back to that strong acid example, you use HCl. So another strong acid, okay. H2SO4. So if it gave up its one of its H and it becomes HSO4, is the HSO4 strong or weak?
So since H2SO4 is, so we're gonna talk about it. 1 second, I have background noise. Give me 1 second, sorry. Apologies for that interruption. So we're going to talk about this a little bit later, but you notice how these have 1 proton that they can transfer essentially. So HCl has 1 hydrogen. This one has also 1 hydrogen that I can remove. There's diprotic, triprotic acids like H2SO4, which have 2 hydrogens, and then they can go into HSO4 and then again into SO4. I'm going to speed through this because we actually are going to cover this later, but in this lecture. Yeah, but essentially, this is both an acid and a base. This is only an acid. This is only a base. This is both, right? Because it can act as a base or an acid to go this way or this way.
Depending on the ability to give up the H's. Okay.
Yeah. Yeah, okay, and it has varying. It's not equally an acid and base. It's sometimes it's stronger one way than the other. But yeah. Okay.
Thank you.
No more questions. Let me just go to the last definition, which is the Lewis definition. Lewis definition is the least tested directly. So concept has a little bit of a different name, or the concept, or like the idea is the same. That you may know better. It's called nucleophile electrophile, if you remember from organic chemistry. The idea is essentially the same as in the Lewis definition, and it focuses exclusively on electrons rather than protons or H plus, OH minus. So acids are known as electron acceptors or nucleophiles, as you may know them, while bases are electron donors or electrophiles, as you may know them. For example, a Lewis base can be NH3 or something like benzene, right? NH3, we talked about why it can be a base, right? From the last definition, because it can accept the proton. Benzene, we usually don't think of it as a base, right? Because it's very weird, right? It's not a typical base that we think of, but it actually is a base because it can actually be an electron donor, right? Because it has the pi bonds, which it can donate as electrons, right? So if you know, remember, a benzene ring looks like this. So these bonds can actually, actually you may see it like this, it's like a circle. These bonds can actually be electron donors, right? So that's why it can be an electrophile. Whereas something, a Lewis acid, can be actually, apart from what we already talked about, something like a metal cation, like Fe3+, or something like this, right? These can actually be considered Lewis acids, even though you would pretty much never think of them as acids in like the normal sense, in the proton sense, because it just doesn't fit with the definition, right? Because they don't really have protons or H pluses to donate, right? Like you would expect, but they actually are acids because they are electron acceptors or nucleophiles. Do you have another question, Opal, or is that from the last time?
Sorry, I meant to lower my hand.
Okay. Does anybody else have any other questions before we move on to the next topic for today? Okay. And if you have any questions, please feel free to put them in the chat. We are monitoring it, okay? Okay, next, we want to talk about pH and pKa, which are two of probably the most important values in all of acids and bases. So how can we measure acidity? Well, there are two measurements involved with acids and bases. The common one is pH. This is the acidity or basicity of a solution, right? If you have a solution of some kind of liquid and you wanted to measure how acidic that solution is, you would use pH. pH 7 means that the solution is perfectly balanced. If you have a pH less than 7, means it's acidic, and the further away it is from 7, the closer it is to 0, the more acidic it is. So a solution with pH of 1 is more acidic than a solution of pH 6. And higher than 7 means it's basic. Again, closer it is to 14, the more basic it is. So pH 13 is more basic than pH 8. A pH 4 a liquid solution of pH 4 would mean that the dissolved in the liquid is more acid than base, and so the solution as a whole is slightly acidic. It doesn't mean that there's only acid in the solution, right? It means that there's acid. It could mean that there's acid and there's base, and when you combine all of that together, overall it's more acidic, and so you get an acidic solution. If we use electrophiles or base electron donors, electrophiles, does it say that? May have mistyped that, yeah. Yeah, I may have mistyped that then these might be switched, right? Because electrophiles are electron acceptors and nucleophiles are electron donors, yeah. Sorry about that. So I will actually make sure in the slides that that is correct. So I'll reiterate again. Nucleophiles are electron donors. Electrophiles, I'll do it in a different color. Electrophiles are electron acceptors. Thank you for catching that.
The acid base part is still correct, right, Mark?
So acids are, no, well, this is correct.
Okay, yeah,
This is correct.
It's okay. I just
And,
wait for the slide. It's okay.
Yeah. So bases are electron donors, nucleophiles. So I'll do it like this. All the black ones like go together. All the red ones go together. If that helps. So acids, electron acceptors, electrophiles, base, electron donors, nucleophiles. But yeah, it will be correct in the slides. I'll make sure. But yeah, this should be the way. Okay. Like I mentioned, Lewis acid is like the least tested one, so don't worry too much about it. But just in case, I'll let you know just so it's more complete of a lecture. Back to what I was saying. So again, pH 4 liquid may have more both acid and base, just more acid than base. So that's why it's overall more acidic or higher concentration of acid than base. And essentially, what pH is a measure of the concentration of H plus. Right, that's what the H in the pH stands for. So if you have a lot of H plus, it goes down to close to 0. So what pH 4 means is that there's a lot of H plus, more so than there is OH minus, or because this kind of uses the Arrhenius definition. So pH and pOH always together make 14. So if you have pH of 4, means you have a lot more H than you have OH, essentially. Okay, moving on. So the other measurement that we use to measure acidity and basicity is pKa. There's also pKb, but that's rarely used. Mainly we use pKa, which measures the acidity, and it refers to the acidic strength of a compound, right? A specific molecule, rather than a solution as a whole. The lower the pKa, the stronger the compound is as an acid. Similar to pH. If you have a lower pH, you're more acidic. pKa kind of goes by similar rules. If something has a very low pKa, that means it's very acidic. For example, the pKa of HCl, which you know is a strong acid, is about -6. So it's a very strong acid. Technically, once you go below 0, you can't really tell, like, experimentally. This is more hypothetical with the negative pKa's. It's more hypothetical because you can't actually go below. You can't actually have negative pKa's experimentally, but people have found out how to do it mathematically or theoretically. And what a negative pKa means is just like really acidic, like a really strong acid, like for example HCl. The pKa of acetic acid, which is the other acid that I was commonly using today's lecture, it's a weak acid. And it has a pKa of about 4 to 5, right? And it varies sometimes, but it's about 4 to 5. So it's a weaker acid, and it's actually classified as a weak acid. CH3NH3 plus, which is the conjugate acid, like I mentioned, it's an acid. It's conjugate acid of a base. It has a pKa of about 11. The reason it's such a weak acid is because NH2 plus is a relatively strong base. So relatively strong base, conjugate acid, relatively weak. This conjugate acid has a pKa of about 11. Okay. And there's actually a specific reason why I picked these two specifically to show you the pKa's of the 4 and the 11. It's because these are very commonly used in actually on the MCAT, because these are the exact two compounds that make up amino acids, right? So this and this are the amino end of the amino acid, and this is the acid part of the amino acid, right? And you'll actually have to memorize these pKa's for when we talk about amino acids this Saturday, I believe. But we'll cover that more on Saturday. But you should know the pKa of this is 4 to 5 about, and the pKa of this is about 11, right? Okay. So what does all this mean? Well, pKa really refers to the pH at which the concentration of acid is equal to the concentration of base of that one compound. Great equation to know is the Henderson-Hasselbalch equation. I believe for the MCAT, you're technically not required to know this equation, but just like I don't think you were technically required in most undergraduate general chemistry courses, but it was very, very highly recommended because this can help you understand it much better, and it can be very useful in solving acid and base problems that you may encounter, even if it's not required. Okay, so the Henderson-Hasselbalch equation is this. This is for acids and this bottom one is for bases. You'll only really be using this top one. I don't really think you'll ever use the bottom one, but just in case you want to learn it. So pH equals pKa plus log concentration of base over concentration of acid. So what I mentioned was pKa is the pH at which the concentration of the acid and the conjugate base are equal. So for example, I mentioned that for NH2 and NH3, right, the pKa is 11. So at pH is 11, they're in the solution of just these molecules, half of the molecules will be in this form, and exactly half of the molecules will be in this form. So you never really see in a solution everything's only in acid form or everything's only in base form, all of the molecules, or all of the atoms are all in base form, or all of the atoms are all in acid form. What you usually see is a mixture. But typically it's very favoring one side. So when we say it's in the acid form, it's because 99.9% of all the molecules are in acid form and very few are in base form. However, when the pH is equal to the pKa of the specific compound, which here we mentioned 11, at pH 11, exactly half of all of the molecules here will be NH2, and exactly half will be NH3+, right? And the reason I said the Henderson-Hasselbalch equation is kind of useful for seeing this is because you know concentration of base and concentration of acid. Like I mentioned, when the pH is equal to the pKa, they're equal. So whatever is on the top is here on the bottom. So this essentially means that pH equals pKa plus log of 1, right? Because anything divided by itself is 1. So log 1. You know that log of 1 is 0, right? So it's just pH equals pKa plus this whole thing is 0. So pH equals pKa, right? That's how you mathematically prove it. And this is also very helpful for determining pH if you know that there's more base or acid, right? If you know that there's more base, you'll have more here on the top, less here on the bottom. You'll have like a positive number, so you'll have like 1.5 or something. Here maybe log of 1.5 is some positive number. I don't know what it is, but it's some positive number. So the pH is slightly higher than the pKa, for example. And that makes sense because there's more base than there is acid. Whereas if you had more acid, log would be, it'll be like log 0.8, 0.8. Log of a decimal less than 1 is negative. So it'll be minus, so it'll be pH equals pK minus a number, which is always less than, right? And same thing can apply for these, but like I mentioned, you don't really see this. And this just uses pKb, pOH, and the acid and base are flipped. Right, notice that? keep track of that. Any questions about this so far before we move on? We're not really, okay, so oxyacids, main thing you have to know about those is that they're usually kind of strong acids. And the way they work is exactly like all the other acids, they just lose the H. The O's don't really get touched. And we actually talked about one already. And we actually will talk about one, H2SO4. It's not oxyacid. There's HP, H3PO4, I think it is. So those work exactly the same. They lose the H because SO4 on its own is negative, or whatever it is negative. Yeah, the focus on the H. So it gets this, like we talked about in proton donors and acceptors. The protons come off. If it's an acid, the protons always come off. All right, any other questions before we move on? Yeah, and I would agree with David. The only time you really focus on anything other than H's is either when you're calculating POH instead of pH, which is weird. You never really do it. Or when you're talking about Lewis definition, which again, very rare, I would say, on the MCAT. That's more safe for organic chemistry when you talk about nucleophiles, electrophiles. Okay. So how can we use all this information, right? We know that for any molecule, if it is a stronger acid than the other molecules around it, it will act as an acid and will donate a proton and thus become deprotonated. So again, we know examples. So if you have HCl, which you know is a strong acid, and it's surrounded by water, right? If you throw some HCl into some water, the HCl is obviously a stronger acid than the water. So it will act as an acid and it will donate a proton to the water. When HCl donates its proton to water, it becomes deprotonated into Cl minus. It gets deprotonated, it becomes Cl minus, and the water becomes protonated because the water acts as a base. And it becomes H3O plus, right? Because it gets a proton, right? And that makes sense to you guys, right? Obviously, Cl is a stronger acid than H2O, so it will act as an acid and it will force H2O to act as a base. And vice versa would also work if you put in a strong base like NaOH into water. It will accept a proton and it will turn the water into OH minus. Okay. We also know that pH is a measure of the acidity of a solution or the amount of acid relative to base in that solution. Therefore, if you drop a molecule into solution of known pH, you can probably tell whether or not it will act as an acid. So the general rule is if the environment is more acidic than a molecule, the molecule will not act as an acid and will remain protonated, right? It will act as a base. But since it's already in its base form, it will just stay the way it is. If it is more acidic, it will act as an acid and deprotonate, and it will change. And this I would highly recommend you to either take a picture of or memorize. If the pH of the solution is greater than the pKa of the molecule, then the molecule becomes deprotonated and acts as an acid. If the pH of the solution is less than the pK, then the molecule is protonated, right? If it's an acid, it stays in its regular form. If it's a base, it will act as a base, right? And this could actually work for both acids and bases because bases will have a really high pKa, right, usually. And if the pH of the solution is greater than that, which is very rare, then the molecule will be deprotonated. So bases will almost never, if it's a strong base, it will almost never be deprotonated. because the pH of the solution just won't be higher than its pKa, right? If you have a pKa of like 20, there's no pH that can be higher than that because the pHs stop at 14. So it'll pretty much be deprotonated in any pH. Whereas if its pH is less than the pKa of the molecule, it's obviously protonated. Okay, Opal, you have a question?
Yes, I'm glad you mentioned this important point about pH in the solution greater than pKa. So for example, those basic amino acid like lysine, and we know that we memorize their pKa like at 6, at that borderline, when it's not quite acidic, it's not quite basic. How do we determine whether it's going to stay protonated or not if it's at that physiological, almost physiological pH?
Right. Well, I don't want to go too in depth with it because actually, 1 second. Tell me, right?
Yeah,
How about you
go.
answer this question first then? Yeah, how about you answer this question first and then I'll answer that question.
Okay.
So this is a poll question, yeah. I'm going to launch the polling. This has 5 answer choices. So I'll launch this poll. Okay. Please take a minute, answer this question. Let me know. Please take another 30 seconds or so to answer this question. Okay, I'm gonna close the poll. And if you didn't get your answers in on time, that's fine. Okay. So actually the results were very mixed. About an equal number of people picked D and C, with B being not actually far behind. I would say the answer is actually B. And we can go over exactly why that is, okay? So we mentioned that if the pH is less than the pKa, that means the environment is more acidic than the actual molecule. If the environment is more acidic than the molecule, then the molecule will be protonated. I'll just write plus for protonated. Doesn't necessarily mean it has a positive charge, which means that it's protonated. And if the pH is greater than the pKa, that means the molecule is more acidic. It will act as an acid, and it will give up its proton. Doesn't necessarily mean, again, it has a negative charge. It just means it. I'm just writing negative to show that it's deprotonated, right? Okay. So let's look at each one individually because I gave you the pKas of all of them. Over here, I told you that the pH is 5, so pKa is 9.47. Well, pKa is greater than pH, therefore it stays this way. Stays exactly the way it is here with a positive charge because it stays protonated. 4.07, well, pKa is less than pH, less than 5. Negative, so deprotonated. So normally it would have an H onto here on this hydrogen, but on this oxygen, but it doesn't because it's deprotonated. Stays exactly the way it is. So right now we have one positive charge, one negative charge. I'm just going to cross them out because they cancel out to make neutral. Over here, again, pK less than pH. This stays negative. Over here, pK is greater than pH. Therefore, it stays positive. Again, positive, negative cancel out. Now we get to these ones, right? Well, this has a pKa of 6, whereas the pH is 5. pH less than pKa is positive, right? So it should be protonated. Well, where would the protonation lie in these? Maybe here, right? This has a site for a proton, for a hydrogen, but look if there are any other sites where it could be protonated, right? And actually, there are. The protonation in this case, and this is called histidine. It's an amino acid that you will have to memorize. All of these are actually amino acids that you will have to memorize. You also have to memorize all of their pKas, right? This is called histidine with a pK of 6, which you should memorize, and you should memorize what it looks like roughly. It actually has, if it was in acidic form, it would actually look like this, where the N would be positive, and it would have an H on the end, on this end specifically, right? Because it has a double bond, which can very easily form, which is kind of reactive, I should say, right? And so it can get another H and become positive. So at pH 5, it actually is protonated, meaning that it has this back, and it's actually +1 +1 for a total of +2. Oh, I shouldn't do that. Does that make sense? Any questions about this for the people that picked C or D? Okay. If there are no questions, I'll move on. So yeah, if pKa is below, if pKa is below, no, if pKa is below pH, it's deprotonated. If pKa is, because if pKa is low, that means it's acidic, right? Whatever is lower is always more acidic, pH and pKa. pKa is lower than pH, that means that means the molecule is more acidic than the solution. If it's more acidic than the solution, it will act as an acid. If it acts as an acid, it will give up its hydrogen and become deprotonated. And somebody mentioned chat, I used the last two and cancel out to neutral. Oh, Yeah, and if you somebody, if you want to type in chat what you meant by I used the last two cancel out to neutral, so I canceled out for you this one and this one canceled out because this one's positive, this one's negative. They canceled. Positive and negative is canceled, so these don't matter. Essentially, they're neutral, but these are both positive, so it's +2. And what I said was protonated doesn't always mean positive. Deprotonated doesn't always mean negative, because this is deprotonated, but it's neutral, and this is protonated, but it's also neutral, right? This is protonated because it solves this hydrogen, but it's neutral. This is deprotonated, but it's also neutral, right? Because it just depends on acid bases. For example, the protonated version of this is H3 plus, which is positive, whereas the deprotonated version of this is COO minus, it's negative, right? Sometimes deprotonated means negative, sometimes deprotonated means neutral. Protonated sometimes means positive, sometimes means neutral. Yeah, it depends on the amino acid, or if we're not talking about biochemistry, if we're talking about just general chemistry, it depends on the molecule. All acidic have pK of not 2. They have, I believe D has 3. We'll cover this actually in the lecture on Saturday, but I believe D has 3, E has 4, or the other way around. One of them has 3, one of them has 4. pKa, the basic ones, R is 9. No, K is 9, R is 11, H is 6. They all have different ones. They all have different pKa's. H is the only outlier with 6. It's the only weird one. R and K are like 10-ish. They're like between 9 and 11. And D are like between like 3 and 4. Somewhere like that. Yeah, but the lecture on Saturday should have like a list of amino acids with their pKa's, and you'll see it, right? That's for the amino acid lecture on Saturday. Any other questions before I move on to titration? If not, the list, it's not, because we're not covering amino acids today. I'm not showing you the list today. That'll be on the list, the lecture on Saturday, which is specifically on biochemistry and amino acids. So yeah, I'll give you the list then. Yeah, or well, actually David will be running that lecture, so he'll have it up. I will be there as well. Yeah. What is titration? So titration. So next we want to move on to titration. Let's see. Let's move in the chat. Before I move on, I want to answer all questions, just because we're moving on to a new section. If pH is below pK, then the molecule is protonated. Yes, exactly. Yeah, that's what I wrote. If the pH is greater than the pKa, molecule is deprotonated. If the pH is less than the pKa, again, remember, if pH is lower, that means it's acidic. If the pH is lower, that means the surroundings, the environment, is more acidic than the molecule. That means the molecule won't become protonated because it'll become protonated because it's acting as a base, right, rather than an acid. If the pKa is lower, that means the molecule is acidic. Exactly, yes. So again, in here, the pH is 5, pKa is 6. That means the pH is lower than the pKa. That means the molecule is protonated. The protonated, this is the deprotonated form. This is the deprotonated form. The protonated form looks like this. and the plus is on the end. This is what the protonated form looks like, right? Because the pH is less than the pKa, it's in the protonated form, which is this. So it's actually positive. Does that make sense? Okay. All right. If you have any other questions, put them in the chat. But I do want to move on because we still have a bit more to go. Yeah, but what you put in the chat is right, and it's exactly like, if you want to go back and look at the lecture notes at the end, or if you want to keep asking questions in the chat, Dave would be happy to answer them. But I do need to move on with the lecture. But you were right with what you put in the chat, and you can go over and look at the lecture notes and kind of figure it out. But yeah, you are correct. Okay, so moving on to titration. So what is titration? Titration is the slow addition of an acid to a base or a base to an acid. Usually it's addition of a base to an acid. That's mostly what I've seen, but it can be the other way around. It's very gradual, meaning literally it's a couple of drops at a time that you're adding. And I'm sure many of you, if you've taken a general chemistry lab, have done a titration experiment before, where you literally opened up the pipette and it dropped a couple of drops of base into the solution of acid, and then you recorded it, and then you just added a couple more drops. What you do is you measure the new pH, you measure the solution, the pH of the solution every single couple of drops, and then record it. So you have put in 2 drops, measure the pH, put in 2 more drops, measure the pH, put in 2 more drops, measure the pH. What you should see is if you're adding base to an acid, so you're adding drops of base to an acid, you should start off at a low pH because the acid's acidic. And then as you add base, it should slowly increase. The more base you add, the more neutral it gets, and the closer to neutral it gets, and the pH rises slowly with each couple of drops. You repeat this until you have many points, and then you plot it as a graph. And this is what the graph looks like. So like I mentioned, right here, you have no base, you just have acid. So it's very acidic, obviously, pH on the y-axis, and concentration of, and the amount of base that you added to the acid is on the x-axis. So on the left, you didn't add any base, you just have acid. So the pH is obviously very acidic. As you add in a little bit more base, you get past, more. And eventually, that happens. Okay. There's 2 important points that you should know on this graph, on this titration curve, which is what it's called. Okay. Titration curve has 2 important points. As this one, which is already labeled for you, it's called the equivalence point. The equivalence point, all titration curves will have this. They'll have a slow increase, then they'll have a big spike, and then back to a slow increase. The equivalence point will always be in the middle of this big spike, in the middle of this vertical line. It'll always be directly in the middle here. Next, you also have the midpoint, which should be, this is the start and this is the equivalence point, should be halfway between the start and the equivalence point. So I'd say roughly about here. This would be the midpoint. And I'll show you a graph where it's labeled as well later. But for now, this is the midpoint. It's halfway between the start of the graph and the equivalence point. And the equivalence point I mentioned is halfway up on this vertical spike. Okay, so this is the midpoint, this is the equivalence point. Midpoint is also sometimes actually called the half equivalence point, which makes it easy to remember, but sometimes you may see it referred to as the midpoint as well. Okay. Now, what is the equivalence point? So the equivalence point is the point at which the acid and base have exactly neutralized each other and canceled each other out. So, for example, if we had, and you guys have all seen this reaction before, HCl plus NaOH go into NaCl plus H2O, right? You combine HCl and NaOH and you just get salt and water. That's how the reaction works, and they neutralize completely. The equivalence point is always the point at which there's no more HCl, there's no more NaOH, there's only salt water, right? And that's because there's an exactly equal amount of HCl and NaOH. They're exactly equal. So because they're exactly equal and it's a 1-to-1 ratio, the reaction proceeds all the way to the right, and all of the HCl is used up, all of the NaOH is used up. You just have salt water. If, for example, you go to the right of the equivalence point, you'll have slightly more NaOH than you will HCl. So all of the HCl will be used up to make salt and water. And most of the NaOH will be used up, but there will still be a little bit of NaOH left because it has nothing to react with, because all of the HCl has been used up. Because there's nothing left to react with, it's just left there, and it makes the solution more basic. That makes sense. So if you look at here, at this point, the amount of NaOH and HCl is exactly even. Starting from here to the right, there's more NaOH. Before this, there's more HCl. When you mix a strong acid and a strong base, like for example, HCl and NaOH, the equivalence point will always be 100% of the time at pH 7. So if you notice here, the equivalence point on the y-axis, it lines up with pH 7. Always with a strong acid and a strong base, it'll always be at 7. For when you mix a weak acid with a strong base, it's much more complicated and involves more math, which will not be asked on the MCAT because the MCAT is a multiple choice test and you only have a certain amount of time and no calculator. So they won't ask you the whole process because it gets complicated, it requires calculators usually, and takes a long time. So you probably won't be asked the whole process, but you may be asked parts of the process. So I'm going to go over some of the parts. Before I do that, wanted to ask this. At about what pH is the equivalence point in this graph? And a lot of times they'll ask you questions exactly like this rather than having you figure out mathematically. They'll have you guesstimate based on a graph. And I would like to ask you right now. The curve should look relatively the same whether you use strong or weak. The curve will look relatively the same. The only difference will be where the equivalence point, where the midpoint is, all of that stuff. But like the shape of the curve will be the same, or roughly the same. Okay, take another 20 or 30 seconds. Okay, I'm gonna stop the poll. Yeah, and 100% of you guys picked D, which is the correct answer. Somebody actually asked a good question, which I was going to go over. This curve is backwards, or it starts off differently. The reason is because that last curve you saw, which is the one you'll probably see more often, it's when you start off with acid and you add in drops of base. In this graph, you start off with a solution of base and you're adding in drops of acid. You can tell because in that other graph, you started off with, when you hadn't added anything, you started off with a very low pH, which signifies you started off with an acid. In this, you start off with a base, which you can see because before you added anything else, it was very high pH, which means basic. And then as you added in drops of acid, it went down. The pH went down because it became, as you added acid, it neutralized and eventually became more acidic. Again, the difference is between strong and weak will be where the equivalence point is, where the midpoint is, all of that stuff. That's what makes the difference between strong, weak, both in acid and in base and whatever. And as for equivalence point, like I mentioned, this is where like the spike or the drop in this case is, and halfway through is about like here roughly, and that corresponds to about pH 6, right? And they won't give you like pH 7 or pH 6.5 or something like that as another option, because they obviously know you're guessing, so they'll give you something easy like 1, 3, 10. Okay, they won't give you anything complicated like that where it's like too hard to guess. Because okay, next I do want to talk about how to do it mathematically slightly. So this is just really memorizing these formulas. So there's these couple formulas that I really want you to know. The first one is pKa equals negative log Ka, or pKb equals negative log Kb, but Ka and pKa are usually what we work with, so it essentially means the same thing. Before I continue, do very quickly want to talk about logs, because when I've taught this lecture before, I noticed people kind of struggled with logs, and even in other lectures where we talk about logs. Logs are very simple. Logs are very easy if you just know how to do it. pK equals negative log Ka. So I'm just going to go over how to do a log real quick. Log is the opposite operation of 10 to the power, right? It's the exact opposite operation. So for example, if you had 5x equals 25, and you wanted to find out what x was equal to, and it's 5 times x, you would do the opposite operation. So you divide both sides by you divide both sides by 5, because that's the opposite operation. You're multiplying by 5, so you want to divide by 5. And that's how you find out what x is equal to. Well, in here, you do exactly the same thing. Like I mentioned, the opposite operation of log is 10 to the power of. So for example, you could do 10 to the power of log Ka. So the opposite operation of both of these would be 10 to the power of 10 to the power of log Ka equals 10 to the power of pKa. Just like if you multiply something by 5 and divide it by 5, you can cancel out. If you take the log of something and 10 to the power of that, you can cancel out. So 10 log cancel out. All you're left with is 10 pKa equal to Ka, essentially. It's actually negative, but yeah. Yes, but I would call it something like an anti-log or inverse of log. Not sure if that's like an official term, but the official term I think is 10 to the power of. I'm not sure if anti-log is like the official term. And if there is something called an anti-log, I'm not sure what it is, because I'm not really a mathematician. That might be like something involved in math or calculus that I don't know, and I don't want to give you a definitive answer because I just don't know. But yeah, 10 to the power of and log are inverse operations, just like multiplication and division are. Same thing actually with e to the power of and ln, right? If you do e to the power of ln x, again, they cancel out and you just get x. So if you did ln x equals y, and you wanted to find out what it was, e to the power of both sides, so Again, e to the ln x cancels out, and you just have x is equal to e to the y power. Okay, and just like here, you have negative Ka is equal to 10 to the pK, but essentially it's like that. I'll give you an example. A Ka could be like 10 to the negative 7th. The pKa of this would very simply be 7, right? Because we talked about Ka is just 10 to that, right? So it'd just be like this. pK is just essentially the exponent of what Ka is, right? And it's negated because in Ka it's negative 7, and pK would be 7. Does that make sense? Does everybody understand how to do logs? Okay.
Sure.
Go ahead.
I was saying yes, sir. Sorry.
Okay, no problem.
Mark, quick question. Do we need to memorize, like you said, the log of 1 is 0, log of 2 is 0.3?
No, no. The only one you should know is log of 1 is 0.
Yeah, but what if they give a number between 2 and 3? Like, I mean, it's simple, you know, log of 2 is 0.3.
Yeah, no, it's
they give
you can't memorize it. You don't have to. You don't.
Okay.
You can't memorize it. You don't have to.
All right. Okay.
Because you'll be able to figure it out on the spot. But if you want to memorize it, I think one of the other tutors, Tim, he suggested memorizing it. I didn't, but he said he did.
Yeah, I just memorized up to 5. That's it. Like
yeah,
if I had an answer.
So up to you. Yeah.
Okay.
All right. So moving on, because that was just a quick detour. Then you have, that was the first formula I think you should know. The second formula, but again, you don't really have to know it, because you can just say, oh, Ka is 10 to the negative 7. Well, pK is 7. If the pK is 7, well, Ka is 10 to the negative 7. Easy. Same thing backwards, but with pKb. This is more important. Kw is equal to Ka times Kb. And Kw is always equal to 10 to the negative 14th. This is like the constant of water, right? This is the constant of water, which is 10 to the negative 14th. And again, K times Kb. When you combine these two, multiply them together, you get 10 to the negative, 10 to the negative 14th. And this actually ties into this part, the pH and the pOH, right? Because again, it goes to 14, but I'll cover that in a second. Next, Ka is actually also, you can relate Ka to concentration of H plus, or Kb to concentration of OH minus. And it's just simply like this. So concentration of H plus times conjugate base over conjugate acid. Usually what they'll ask you to find, they'll give you a Ka, they'll give you the concentration of base and acid, they'll try and ask you to find this. So this is usually what you'll be solving for using this equation. Simply just memorize it. There's nothing else to really say. Just memorize it. Kb is the same thing, except you're finding concentration of OH minus, and you're flipping conjugate acid or base. Very simple. And then you have here, which is pH equals negative log of concentration of acid. Again, it works exactly the same way as pKa and Ka. Concentration of acid is 10 to the negative 10. pH is 10. If the concentration of acid is 10 to the negative 3, pH 3. That also tells you why lower pH is more acidic, higher pH is more basic, right? If you have a pH of 3, that means the concentration of H plus is 10 to the negative 3. Whereas if you have a pH of 11, H plus is 10 to the negative 11. 10 to the negative 11, and I'll actually write it out. 10 to the negative 11th is smaller than 10 to the negative 3, right? So a pH of 3 means this. So you actually have more H plus than if you had a pH of 11 overall. So that's what that means, right? And that's how that relates mathematically. But again, it's the same exact idea, but you may be given, like, say something like a Ka value and asked to find the pH, and this is how you would do it. you would just find the concentration of H plus, and then from there you could find the pH. And again, just like with this, pH plus POH is always equal to 14, right? Because POH is just the concentration of negative OH. And you can, if you wanted to, I'm not going to go over it because it's just a lot of unnecessary writing, but you could actually just prove this using all of these formulas. You could actually prove this formula. But if you guys want to do it, I encourage you to do it on your own. If not, take my word for it. It does prove it if you cancel out. Otherwise, yeah, I would just honestly recommend memorizing this whole list of formulas. Some of these, like this one, and this one, even to an extent this one, very easy to remember or think about. So you don't, not really much effort required. These are a little bit harder. Those I recommend memorizing. But yeah, you may be asked that. Okay. Let me see what time it is. Okay. So yeah, well, we can do this full question then. Yeah, it's also, yeah, with Ka and pK, it's the same thing. Having a smaller number is actually means more acidic because concentration of H plus more, right? Okay, I'm gonna relaunch the poll. See if you can do this one fairly quickly. I'll give you guys like a minute or so for this one. So see if you can do it quick. Okay. Take another maybe 30 to 40 seconds. Get transfers in. Okay. Okay, I'm gonna end the poll. I know that was quick and most of you probably didn't get a chance to vote, but I just wanted to kind of like do this quickly because we do still have a bit more and I don't want to go too far, too late. So the majority of people picked answer choice B, and I would agree. I think it's B because, again, we have Ka of 1, and I'll just rewrite it 10 to the 0th power. That means pKa is 0, right? Because I just told you pKa is just the exponent. If you do 10 to the power of it, it's just the exponent. So pKa would be 0, actually would be negative. Oh, sorry, it would be negative 0, but which is also 0. So pKa is 0. I mentioned the lower the pKa, the more acidic it is. If you have a pKa of 0, that's fairly acidic. I mentioned you can't actually go below pKa of 0 in experimental real life conditions, but there are, like HCl has a pKa lower than 0, has like -6. It's just because people like mathematically determined it. I think something similar to this actually, but I'm not exactly sure what Ka, like how to experimentally get Ka, but I'm sure there's a process and that's how they experimentally determined what pK of a negative strong acid is. But regardless, it would be pK would be 0, which is fairly acidic. So solution containing that would be less than 7. Okay. And again, you would use these. Okay. Okay, this is one of the last topics for today. I believe we have one more after this, but first I want to talk about what are multiprotic acids. So this is actually something we actually covered on earlier. H2SO4 goes into HSO4, goes into SO4. So most acids that we've talked about, like HCl, acetic acid, they have one H. They go straight from protonated to deprotonated. One H, that's it. Mainly, they have one protic event, but because they only have one H. But there are acids that are diprotic or triprotic, meaning that they can be deprotonated 2 or 3 times. Like for example, H2SO4 has 2 H's, can be actually deprotonated both times because it can lose both H's. It's actually minus. This is 2 minus. So it can lose its H once and become HSO4. Then this HSO4 can actually lose its H again, become SO4 minus. Again, monoprotic HCl, sulfuric acid H2SO4 is diprotic, something like phosphoric acid H3PO4 is triprotic because you can go H2, H, and PO4. As for acid and bases, this is only an acid. This is both an acid and a base, right? Because H2PO4 can act as an acid and turn into HPO4 to this, or it can act as a base and turn back into this, right? So it can go both ways. And then again, HPO4 2 minus is also an acid and base. It can go back to H2SO4, or it can complete and become an acid and become PO4. And this is only a base. PO4 can't get more deprotonated. It can only go backwards to become, it can only act as a base and go backwards. Because even though they're both acids and bases, they don't have to be equally acids and bases. They can be stronger acids than they are bases, or stronger bases than they are acids. Not exactly sure with the numbers, and if they ever want you to know the numbers, they'll tell you. They won't really ask you to memorize it, so I wouldn't worry about it. But if you're curious, you can look it up, and it varies from obviously from molecule to molecule. So H2SO4 and HSO4 might be different than H2PO4 and HPO4. Okay, but that's the general idea. Things can get deprotonated multiple times, and the way you would know that is if it has multiple H's on it, right? That can dissociate. So for example, like something like acetic acid, which has the formula CH3COOH. Technically, it does have multiple H's, right? Right here it has 3 H's, but these are not acidic H's. They can't actually come off. So it won't count as like a quad protic or whatever, or multiprotic acid, because it can't, these H's can't come off. Only this H can come off. And the way you would know that is if it's attached to a carbon, it most likely can't come off. If an H is attached to a carbon, it most likely can't come off. It's very rare that it can act as an acid if it's attached to a carbon directly. And that's because the pK of those hydrogens specifically would be like, I don't know, like 50 or something, and it would be really, really, really hard to get them off. Now I want to talk about multiprotic acids titration curves. So this could be the titration curve of a diprotic acid, right? Because it has 2 equivalents, because it has 2 deprotonation events. So for example, this is probably H2SO4 or something similar, something that's diprotic. Again, it starts off in H2SO4, then slowly it gets turned into neutralized, and at about this point, or somewhere roughly there, there is no more H2SO4. There is pretty much only HSO4 at this point. Pretty much all of the H2SO4 has been converted into HS4 by this point. Then HSO4 keeps going, and then at about say I accidentally stopped sharing the screen. At about, oh, I have to draw that. Sorry about that. Sorry, it's glitching out on me. But you guys get it, like at this point it's HSO4. At this point it's about only SO4 minus 2 minus. This is minus, right? Next I want to talk about these points, right? We talk about titration curves has 2 important points. We talk about the equivalence point, and notice how here the equivalence point is less than 7 because it's not strong acid and strong base, right? Not exactly, but otherwise, we talk about this, the midpoint, which is halfway between the start and the equivalence point, right? And if we consider like this the start and this the next equivalence point, so the second midpoint would be here. The midpoint is when the concentration of acid and conjugate base are equal, right? With the equivalence point, it's considering the acid with the amount of base total, right? With the base you're adding. However, with the midpoint, it's more talking about itself. So we know that at the start, it's H2SO4 only at this start. At this endpoint right here, it's only HSO4. So as you rode this line, all of the H2SO4 would have slowly gotten converted, like one atom at a time, essentially, into HSO4. At this point, the midpoint, 1, the amount of H2SO4 and the amount of HSO4 are equal. So what that means is, at that point, exactly 1/2 of the original H2SO4 has already been converted. The other half is yet to be converted. It hasn't changed yet, but it will be if you keep adding more base. But at the midpoint, exactly 1/2 has already been changed into its alternate form, right? And again, in this midpoint, it would be half of HSO4 has been converted to just SO4, right? So the concentration of, at this point, concentration of HSO4 and SO4 are equal, okay? Is that clear? Does everybody understand? Any questions about this at all?
Wait, so your equivalence point was just a tad bit higher than what they're pointing to, saying first equivalence point. Do we go off your cute little circle equivalence point, or where they're pointing saying that's the equivalence point?
Equivalence point, and well, my circle was not the equivalence point.
What?
How
much?
It was not the equivalence. It was a rough estimate. It was basically, I said at this point, all of the H2SO4 has turned into HSO4.
Okay.
Right, at the equivalence point, that might not have happened. The way you can actually tell that is it should be when this curve at the top of this curve, when it actually like flat lines out again. So you see here it like flat lines out because it goes back to the start, right? This is like, if you want to think of it like this way, it went like this, right? Like that.
Okay,
so if you shifted the curve that way, like the scope. Okay.
Okay, cool. Okay.
Yeah.
And so the equivalence point is what again then? It's just kind of where it makes that turning point and gets you ready to make that turning point, or?
The equivalence point is when, so you know that you originally had acid. Yeah. It's when you had the original acid and the base that you're dropping in, the droplets of base you're adding in, when those cancel out each other perfectly. Right?
Okay.
Yeah, and essentially at that point, it will be neutralized. You'll have no acid and no base in the solution at all. You'll only have salt and water. Whatever salt it is and water, yeah.
Okay, so we do NaCl and H2SO4.
Exactly, yeah.
Okay. Okay. Cool.
HCl and NaOH, and you have
That
NaCl and water. Yeah.
Okay.
You just have salt water, but if you have different, obviously, acids and bases, it would have different salts. But yeah. Okay. Yeah, and so that's the equivalence point. Midpoint is when it's conversion of the actual molecule itself. Equivalence point refers to the acid and the base that you're adding in. Midpoint refers to the acid converting itself into base, right? So you know that the acid, H2SO4, converts itself as time goes on into base, into a conjugate base, HSO4. It gets deprotonated and yeah. Okay. All right.
So Mark,
will
the midpoint be like 25%? Since the equivalence would probably be 50% of the species, would the midpoint be 25, like midpoint 1 here? In the
no, so midpoint 1 would be when exact, okay.
25%
so
maybe?
Again, at this, no, exactly, okay, so H2SO4. So you started off with H2SO4 right here. And then I mentioned, at the start here, you have H2SO4 only, nothing else. At this point, you have nothing else except HSO4, right? Does that make sense so far?
Yes. Mm-hmm.
Okay. As you're going along this line, this H2SO4 has to be converted to HSO4, right?
Yes.
Okay.
Yes. Mm-hmm.
This midpoint is when exactly 1/2 of the H2SO4 has been converted into HSO4. So if you started off with, say, yeah, so these aren't real numbers, but just to make it easier, if you started off with 10 H2SO4 here, you have 10 HSO4 here. This midpoint would be when 1/2 of the H2SO4 has been converted. So 5 of the H2SO4 have become HSO4, so you have 5 of these, but 5 haven't been converted, so you still have 5 of these, exactly half. 5 is equal to 5. Whenever you have
okay, and
converted,
so then at equivalence point, what is that now? 5 and what? What would the concentrations be?
That's not determinable. That's not something that you could determine.
Okay.
That's not, the equivalence point is not related to the internal stuff. It would most likely be almost all of it. It will most likely be probably close to like 8.2, 8.5, 1.5, something like that. But it's not really determinable because it's not really exactly how it works. But it would be close to 0. It would be close to 0. Okay. Okay, moving on. This question, I'm actually just going to skip this question. I'll give you guys like 2 seconds to think about it just by looking at it. But I will slowly start to go over it because we don't have enough time. If you consider the titration curve in which an acid is treated with a base, so again, titration, acid base is monoprotic, so it's only one H. Which defined compounds could be the acid that's being titrated? Well, this involves a lot of your knowledge that we talked about today. Again, it only has one curve, so it's monoprotic, right? It only has one protonation event. If it was diprotic or triprotic, it would look something like this, right? Or if it was triprotic, it would look like more like this, right? It would have multiple curves. But since it's one curve, you know, it can't be H2SO4, which is diprotic. The others it can be because the others are monoprotic. Next, you would look at the equivalence point. So the equivalence point would be somewhere here, maybe, right? Somewhere like roughly around there. So that's about, I would say 9. Remember that I said that if you add a strong acid and a strong base for titration, the equivalence point is always at pH 7. In this case, it's pH 9. They told you that they're adding in a strong base, NaOH. So that means if this was a strong acid that they were adding in, the equivalence point would be at 7. since it's at 9, it can't be a strong acid. It has to be a weak acid. HCl is out because HCl is a strong acid, right? And we knew that based on the equivalence point. Lastly, and I guess I slightly didn't cover it, but you could have made the leap. When I said that for the midpoint, which is, I would say about here, which is equal to pH 5, which is equal to pH 5. The midpoint is when exactly 1/2 of the conjugate base has turned into acid. We've actually seen that before, where the conjugate base and the conjugate acid are equal. We saw that in the Henderson-Hasselbalch equation. Remember, where it had log base over acid, right? And when base over acid were equal, that's when the pH equals the pKa. When this happens, when they're equal, pH equals pKa, if you guys remember that from earlier, right? What that means is, since the midpoint is the point at which the pH and the pKa are equal, and we know that the pH is equal to 5 at the midpoint, the pKa of this solution must be 5 as well. That's because at the midpoint, the pH is equal to the pKa. pH we know is 5. We know 5, we can substitute in 5 equals pKa, pKa equals 5. They give us the Ka values, right? Of all of these. We know the conversion rates of Ka to pKa. This has a Ka of maybe 5-ish. It's not exact because you're multiplying by 1.5, but 1.8, but it's about 5. This would be maybe 4.5, and this would be 10.5, something like that. Since they gave us the Ka value, we know that the pKa's are 5, 4.5, and 10.5 of these three respectively. We are looking for a pKa of 5. Out of these, this one is the closest. So I would say the answer is C. Because the Ka, from the Ka you can find a pKa. The pKa you know has to be 5. This was the closest one that's 5. 4.5 is close, but 4.5, if you look at the graph, 4.5 would be somewhere right here, which is definitely not in the midpoint, right? Even though 4.5 and 5 are close, and I said they usually won't give you something close, they're asking you to estimate, they made it easy enough to differentiate because 5 is over here, right? You can draw the line. 4.5 would be somewhere like right here, which is very clearly like far away from the midpoint, right? It's very far away. So that's why I would say the answer would be C. Does everybody understand? Does anybody have any questions? Does anybody want me to repeat anything? If not, I'm going to move on. So again, first you can cancel out any diproducts. Then you can cancel out any strong acids because the equivalence point. Then you have to use the information they give you, which is the Ka. From there you can find the pKa. Because you know that the midpoint is where the pH and the pKa are equal to. As if you know the pH, which you do, it's 5. You can find out what the pKa of this acid is. And then you just have to match which of these answer choices has the closest pKa, which is C. Okay. Last thing I want to go over is lab testing. Okay. So in labs, and I'm sure some of you have done this, we have this thing called a buffer. A buffer is a compound that's used in many experiments, especially in biology, in order to maintain the pH at a certain level. When you have a test tube and you have reactions going on in the test tube, biological or chemical, they may produce products that are acidic or basic, and those products would change the pH of the solution. However, in biology, and since we're trying to study biology, the closest way to do so in a test tube is to make sure that the pH doesn't change, because our body also has natural buffers, and in our body, the pH is very well controlled. It never really fluctuates. So if we had a test tube in which we were trying to test a biological reaction, and as the reaction was going on, the pH changed suddenly, it wouldn't really give us accurate results to the experiment, because that doesn't happen in our body. The pH doesn't change. In order to do that, we use this thing called buffers. Buffers, their job is to resist changes in pH. They make sure that the pH doesn't change of the solution. Some of the most common buffers that we actually use are weak acids and bases, in biology at least. This is because when the target pH of the experiment is near the pKa of the acid or base, it's not easy to change the pH. I can actually show you this visually using this titration curve. So remember that titration curve is what happens when you have a solution and then you're slowly adding in strong base, right? We mentioned that the midpoint is equal to the pKa, right, of a solution, right? So notice how at the midpoint, if you use the buffer, so we were at pH 5 at this pH, and we had carboxylic acid, which let's say, for example, is this one. And it has a pKa of 5 and a midpoint at pH equals 5. If you add in a little bit more base and go very slight, this picture, just look at the midpoint. Again, at pH 5 or pH whatever this is, and then you added in a little bit of strong base, you moved to the right, just a little bit. Well, what's the pH now? It's basically the same. What happens if you move pH a little bit to the left? If you add in a little bit more acid and you move the graph a little bit to the left from the midpoint? Well, again, draw the line, pH unchanged. At this range, it's almost a horizontal, and you can see here very clearly. At this point, it's almost a horizontal line. So that means if you add in a little bit of base or a little bit of acid, the pH, the Y component, won't change essentially. What that means is it's very resistant to changes. Whereas, for example, if we use something here, if you change a little bit, add in a little bit base, you go over here, which is a little bit to the right, well, the pH changes by like a whole value. Or if you go a little bit to the left and here, you change the pH by a lot, right? So at this area around the equivalence point, it's very bad as a buffer, because small changes in acid-base concentration lead to huge changes in pH. Small changes in pH in this region, the midpoint, or it's actually also called the buffer zone in biology. So it's called the midpoint, half equivalence point, or sometimes the buffer region. This buffer region is very good for, as the name would imply, buffers, because small changes in acid-base concentration have essentially no change in pH concentration, and they are very helpful for maintaining a certain pH that you want. So for example, if you want to maintain your pH in the test tube at pH 7 the entire experiment, you would find a weak acid or a weak base that has a pKa of 7, and you would use that as a buffer, and it would prevent any changes from in pH away from pH 7, either to pH 8 or to pH 6, in either direction. If you wanted your reaction to be at pH 11, you would use a weak acid or weak base that had a pKa of 11. Again, does that make sense? Does everybody understand what a buffer is? Or how we determine what is and what isn't a good buffer. So a good buffer would have a pKa equivalent to the ideal pH that we want to keep the experiment at. Okay, next lab technique that I want to talk about are color change tests. If we want to measure the pH of a solution, one way we could do it is through through a pH meter, but that's a little bit of more recent technology and may not always be convenient, may be sometimes difficult, may be somewhat inaccurate. Before this, we commonly used pH color change tests. One common way is to use a litmus test. A litmus test involves taking part of a special litmus paper, so it's literally like a scrap of small paper, and it puts it into the solution, and if the paper actually changes color, that indicates what pH it is at. So a litmus paper normally starts off as one color, say red, if you had red litmus paper, and then if you, or I have an example here, if you had blue litmus paper, if it comes into an acidic solution that has a pH below 5, when the blue litmus paper comes in contact with the solution, it will change color to red. So you dip the litmus paper in the solution. If it changes to red, you know that the solution is acidic, below pH 5. If the pH of the solution is 7, you dip the paper in, you dip it out, it's still blue. That means you know it's above pH 5. Very simple test, very easy. A more complicated and I would say a more useful test from litmus paper is an indicator chemical, right? We also use these commonly. So the paper, I believe usually it's blue. I believe litmus paper is usually blue, but it can really be any color, and as long as it changes color, it's okay, but usually I think they're blue. Apart from litmus paper, other tests may include dropping an indicator chemical that similarly changes color based on pH into the solution. However, instead of a piece of paper, it's actually like a chemical, like almost like a food dye that you drop into your solution. So for example, there's this indicator called bromothymol blue. If you drop bromothymol blue into a solution, if the pH of the solution is greater than 7, it will turn a deep blue. If the pH is between 6 and 7, then the bromothymol blue will turn green. If the pH is below 6, the solution will turn yellow from the bromothymol blue. Based on this, you would know if you dropped, say, some of the chemical into any solution, you'd be able to tell if it was acidic, basic, or neutral. What sometimes they may give you is an effective range for the indicator. So for example, the range for bromothymol blue is pH 5 to pH 7.5. This doesn't mean that it doesn't work on pHs higher or lower than that, and it actually will. What it means is that anything out of the range, you wouldn't be able to tell the difference. So for example, if you dropped it into a pH of 5, it would turn a deep yellow. If you dropped it into pH 2, it would turn the exact same shade of yellow. Therefore, just using the indicator, you wouldn't be able to tell the difference between a solution of pH 2 and pH 5. But between 5 and 7.5, it actually has various shades. So if you took pHs of 5, 5.5, 6, 6.5, 7, 7.5, and dropped bromothymol blue into each of them, all of them would be different shades, and you would be able to tell exactly which one is 5, 5.5, 6, 6.5, 7, and 7.5, because they're within the indicated range. So because they'd be different shades, you'd be able to tell where it is on the pH spectrum. Again, anything pH 5 or below will be the same shade of yellow regardless of what the pH is, and all pH greater than 7 will be the same shade of blue. But pH 6.5 and 7.5 will have different shades of blue-green. So you'll be able to differentiate 6.5 from 7.5, right? That's what effective range means. If the effective range they give you is 2 to 4, that means anything below 2 or anything above 4 will all be the same shade. But between 2 and 4, it'll be like a spectrum. And you'll be able to tell the color differences, and you'll be able to tell what pH it exactly is. Any questions? Because I believe this is the last slide. Any questions before we end for today? If not, thank you guys very much for joining us. Have a great rest of your night.